Alrighty guys, here we go. This is my problem solving video, and yes, my name is Bela Soderquist. This is for Physics 1. Alright, so first we're going to start out with a little bit of a video inside of a video. Friend here. Legolas here takes a shield and fully slides down this staircase with it. And what I wanted to know is, what is the coefficient for kinetic friction between the shield and the staircase? So, as you can see, he just kind of slides down because he is the greatest of all time. Anyways, so here's our problem. Legolas, being an elf, is quite light, weighing in at about 59 kilograms, and the shield weighs about 8 kilograms. Additionally, he starts at the top of the staircase with an initial speed of about 1.5 meters per second. If the staircase is 3.5 meters in length, descends at a 30-degree angle below the horizontal, and the shield completely stops at the bottom of the stairs. I know, unrealistic, but hey, this is the Lord of the Rings, baby. What is the coefficient of kinetic friction between the stairs and the shield? Assume that the gravity of Middle Earth is the same as regular Earth, just to make things easier. Alright, so first of all, we start out always with our free body diagram. So right up here, I just drew out a little bit of an easier sort of like perspective on the problem we're trying to solve here. So we've got 30 degrees below the horizontal. Here's the shield initially with a velocity of 1.5. We know all of this stops down here, 3.5 meters in length. Over here is our free body diagram at the beginning. We have the normal force, which is perpendicular to the surface here. We've got the force of kinetic friction that is working against Legolas's shield surfing, and then down here is the force of gravity pulling him down. So first things first. Oh no, we need to go back a slide. First things first, we're going to adjust our free body diagram so that only the gravity is at an angle. This is going to make things a little bit easier for us. So now we're going to write out our equation. So first off, we're going to use the kinematic equation that is independent of time. So our final velocity squared is equal to our initial velocity squared plus 2 times our acceleration times our distance traveled. So we're going to substitute our values in, or otherwise known as our unknowns. So final velocity 0, initial velocity 1.5. Here, note this negative sign. So up here it's positive, down here it's minus. Why is that? Well, that's because acceleration is working against us here. He is slowing down, which means, which makes sense because our initial velocity is greater than our final. So that's important to know here. So minus 2 times our acceleration, which we don't know yet, times our distance traveled, which is 3.5 meters. And it's always a good idea to keep track of your units, but for simplicity, I just decided not to. That is not a good idea. But anyways, so then you rearrange this equation to solve for A, and I got negative 0.32 meters per second, which tracks. So next up, now we solve for our coefficient of friction. So we know from earlier that our acceleration is at negative 0.32 meters per second. But our force due to kinetic friction is equal to our force of gravity that is parallel to our staircase, otherwise known as, in this case, the gravity going in the same direction as this arrow here, just going down this way, minus our friction, our force of friction, which is here. Q stands for the coefficient of kinetic friction, and N standing for the normal force. However, we can just ignore the mass in the normal force and our force of gravity here because it's all going to cancel out anyways. So that leaves us with 9.8 times the sine of 30 degrees minus our coefficient of kinetic friction times 9.8 times the cosine of 30 degrees equals our acceleration up here, which we're really just looking for like the magnitude here. The negative sign is only really up here to tell us the direction in which way the acceleration is going, so it doesn't really matter down here. So after this, we rearrange the equation to solve for this coefficient of kinetic friction, which we see here ends up being about 0.54, which that is below 1, which is good, and the standard coefficient for kinetic friction between like wood in wood or wood in metal or like metal in stone is roughly in that 0.4 to 0.7 range. So 0.54 makes sense. So yes, our coefficient of kinetic friction between the shield and the staircase here